All right, so here I am with those three equations I gave you, and I'm going to try and get as much information as I can to go ahead and put it on the graph. Might be a little less confusing now because we're going to do it all at one time. All right, so first off, I can see I have a quadratic. That quadratic tells me I'm going to end up with a parabola. Right off the bat, I'm expecting a parabola on this thing right here. So to draw a parabola, usually all I need is the 3 points. I need the minimum or maximum. That's found in the first derivative. The x-intercepts. And that usually tells me whether it's concave up or concave down. But I can use the second derivative also. Okay, so that's not too bad. The first derivative is going to be 6x plus 10. If I set that equal to 0, I get negative 10 equals 6x. So x would be negative 5/3. So I know that I have a minimum or maximum at negative 5/3. I've just got to figure out which one it is. All right, so I've got negative 5/3. I'm going to substitute in a number less than that. So let's look at f of, I don't know, negative 2. So negative 2 squared would be 4 times 3 is 12. 12 plus negative 20 and negative 8, that's going to get me a negative number. I don't even need to know what it is, I just need to know it's negative. Let's go ahead and substitute in a number here and see what we get. Number that's larger than negative 5/3. If we go larger than 5/3, let's say negative 1. So negative 1, so that's going to be 3. And negative 10 and negative 8. I'm sorry. Woohoo. Messed up. I did it again. I need to label these. Remember I did that on the last problem, right? I need to substitute these numbers into the first derivative. So let's put negative 2 into the first derivative. 6 times negative 2 is negative 12 plus 10 is negative. Now let's substitute in a number that's larger. I was given that funny look because something wasn't working out in my head. Because I like to use 0. And when I put 0 in here, I got a negative number. That didn't make sense. But I need to be putting it into the first derivative. 6 times 0 is 0 plus 10 gives me positive. So I know this means I'm going from a negatively sloped curve to a positively sloped curve. So that's going to be a minimum. So my minimum is that x equals negative 5/3. Now I go back to the original function. And I've already calculated this because it was an ugly fraction. The y value that matches that is negative 49/3. Okay, so I have a minimum at negative 5/3. That's negative 3/3, negative 6/3, so that's negative 5/3, and negative 49/3. 16, so let's go 4, 4, 4, 4. Let's go right here. There's my minimum. I'm counting this as negative 4, and I'm counting that as negative 1, okay? All right, so we found our minimum point. Let's see what happens here. I could find a y-intercept, right? The y-intercept is when x equals 0. So if x equals 0, the y-intercept is negative 8. Oh, well, that would fall right here. So it looks like this thing is concave up. Let's do the second derivative just to make sure. Second derivative equals 6. Well, that's always positive. So that means it is concave up, okay? So just to be specific about where we are actually intersecting the x-axis, let's go ahead and factor the thing. So if I factor it, let's see if I can factor this without a calculator here. So what multiplies to negative 24 and adds up to 10? I believe there's a 6 and a 4 in there, right? Okay, let's a little bit of practice here while we can do it on, why did that all come out black? That was stupid. A little bit of practice on some factoring because I know how much you guys like that. Let's go ahead and try this again. And let's try and get a white space to write on. There we go. All right, so let's go ahead and factor this thing. Okay, so So I said 3x squared, and I said 6 and 4, right? But one of those would, no, that's not going to work. 12 and 2 is going to work because one has to be positive and one has to be negative, right? So if I did a positive 12 and a negative 2, that should factor for us. So I can pull out a 3x here, which would get me x plus 4. And I can pull out a negative 2 here, which would get me x plus 4. Yep, it works. So one of my factors is 3x minus 2, and the other factor is x plus 4. So that means my x-intercepts are negative 4 and positive 2/3. All right. That was nice. It wasn't fraction. I mean, well, it was 1 decimal. Not too bad, though. So the x-intercepts are at negative 4, 1, 2, 3, 4, and positive 2/3. So now I can start actually making my parabola. Okay. So what IB would judge you on is that it is an approximate shape of a parabola. It is concave up. The minimum is in approximately the right position, and that the x-intercepts are in the approximately the right position. All right. So the next one, what we're looking at here, right off the bat, I see a rational expression. Oh, Lord. See a rational expression, which means I'm going to have some asymptotes going on. Okay, so my horizontal asymptote is found by doing the, looking at the degrees. The degrees match, so I look at the leading coefficients, and it's 1 over 1. So horizontal asymptote is y equals 1. The vertical asymptote is found by getting the zeros of the denominator, and the 0 of this denominator is x equals 4. So I've got my 2 asymptotes already. So let's go ahead and see if we can find out, well, I got an x-intercept too, actually. What would make the original function equal 0? So what would make it equal 0? Well, if I put a negative 2 in here, it would make the numerator equal 0, and that's all we need. So I've got an x-intercept also. So I'm doing really well. What I would like to do is go ahead and find the first derivative of this. Now, this isn't so pretty because we are looking at the quotient rule, and I just don't like the quotient rule. That's why I don't think it's pretty. I get confused with it. So anyway, to do the quotient rule, I have to do v, which is x minus 4, times the derivative of u, which is 1, minus u, which is x plus 2, times the derivative of v, which is 1. Now that's not too bad because we had a bunch of 1s in there. And then we take this numerator, the v, and we square it. So that means my first derivative is equal to x minus x, no big deal there, and negative 4 minus 2. Did I do that backwards? I might have done that backwards. Negative 4 minus 2 would get me negative 6. Okay? I don't think it's going to, I think I did it backwards on my paper, not here. And then we have x minus 4 quantity squared. So that's my first derivative. From that, I'm going to do my second derivative because I'm looking for concavity here. Where my two things intersect at the 0.41, that's where my asymptotes intersect. So I need to kind of see before and after 4 what's going to happen, whether they're concave up or concave down. So my second derivative is equal to v, which is x minus 4 quantity squared, times the derivative of u, which is 0, minus u, which is negative 6, times the derivative of v, which I've got to employ the chain rule to do this. So it's 2 times x, so it's just 2 times x minus 4 to the first power. Okay, and that's all going to be divided by x minus 4 to the 4th power now. So again, let's see if we can cancel out one of these powers, and I can. Here comes an x minus 4 out of here. This one goes down to 3, and this one goes down to 1. So this term is equal to 0, so really I'm looking at a positive 12 on top, and I'm looking at x minus 4 cubed on bottom. Okay, so what I want to find out is concavity here, and I want to see it on either side of this asymptote. So I'm going to put a 4 here. So if I put the number 5 in here, I've got 5 minus 4, which is 1, cubed is positive. Positive divided by positive gives me a positive here. If I put in 3 here to see what the concavity is on this side, 3 minus 4 is negative, 1 cubed is negative, 12 divided by negative is negative. So I can figure out now the concavity for it. So what that means, let's go ahead and do some graphing now. All right, so my asymptotes are at y equals 1, right across here, and I'm just going to count each block as 1 now. And x equals 4, 1, 2, 3, 4 here. Actually, you know what? That's too far. Let's count each block as 2's. There we go. So let's count each block as 2 across, but 1's up and down. Okay, so 4. That's going to put it right there. All right, and it also told me that I had an x-intercept at -2, 0. So I'm hitting right here. And this side of 4 is concave down. And this side of 4 is concave up. Okay. All right, now this one over here, the lovely e to the x. We love those. But actually, this is not bad because I'm going to rewrite this function as 1/2 e to the x minus 1/2 e to the negative x. The reason I did this was so that I could just do the power rule here. So the first derivative is equal to, well, the coefficient comes down and multiplies. That's just 1. So that's 1/2 e to the x. Coefficient here is -1 multiplies. So I get plus 1/2 e to the negative x. All right. So that gets me a second derivative of 1/2 e to the x minus 1/2 e to the negative x. And I think from that point on, it would just keep alternating. All right, so what that tells me is that I have, if I put 0 in here, 0, right? 0, something to the 0 power is 1, minus 1, that would equal 0. So I have a intercept here at 0, 0. Great. What it also tells me is the second derivative. If I put a 1 in here, I'm sorry, second derivative. If I put a 0 in here, this turns into 1/2. If I put a 0 in here, this turns into minus 1/2. So that would be it. So that's also my point of inflection. And then if I'm looking at my second derivative, what happens after the second derivative, if I put in the number 1, I'm going to get a positive. If I put in the number 1, and I can check this in my calculator, I'm going to get a positive here. If I put in a -1, I'm going to get a negative here. So that means on this side, we're concave down, and on this side, we're concave up. So that's what your graph will look like. And you can always do these, like if you're doing them on your own, you can always go and check them in your calculator on Desmos and make sure that you've graphed them correctly, make sure you came up with the right points. All right, so now we're going to go and look at comparing some graphs from the original to the first derivative to the second derivative.